first of all, I'm going to apologize in advance. I'm a little unwell. There will be episodes of me sneezing and of me coughing throughout the stream, but I'm committed to doing this, so I shall be doing it. And yeah, I think that's the disclaimer out of the way. So, thank you for showing up today. Um, the intention today was to explore is to is to. The intention today is to explore power management, especially in Zephyr. And our target of choice today is uh, NRF 52840 Dongle, which is a small, I mean, it's a development board for the NRF 52840 system on chip. And the reason I'm doing this is I have an upcoming audio project that's going to be rather intensive, and I need to familiarize myself with this system on chip. And plus that, I need to get ready to do the I need to get ready and get familiar with radio and audio, and then doing both of them, which are both very heavy processes on a small disconnected chip. So that's a bit of excuse me, that's a bit of a challenge. Anyways, we'll get through it. So I think before before we uh, how do I say for me saying Apple there. Uh, Sorry about that. So before we commence, let's just put a backstory. I chose this SoC because it's already chosen for the project I'm going to be working on. And anyways, it's a good collection of the sorts of peripherals we want together. Um, that's the motivation for this. And anyway, not even anyway, this system on chip happens to be very popular for basically low power wireless consumer applications, and that way makes it more interesting to explore this, and it has a very wide user usability. So basically, what we're going to do is just run through. I might go up. I might end up renaming the stream, but because it might end up just be NRF without doing some Zephyr stuff. But if you wait long enough, maybe towards the end, we might end up doing some Zephyr stuff, which will be power management. Uh, it's rather simple and straightforward. I think to understand what you're doing is harder than to do what you need to do. So let's quickly just explore this system on chip that we need to look at today, and then we can make up some objectives of how to go through it, how to kind of break this down and stuff. So I'll quickly go through the first paragraph in the document ahead of me, and then probably change to one or two more documents, since this one is not as comprehensive as we need. So the NRF52840 dongle is a small low-cost USB dongle for Bluetooth, low energy Bluetooth mesh thread, Zigbee, and 802.15.4 and 2.4 gigahertz applications on the aforementioned system on chip. The dongle is perfect target hardware for use with the NRF Connect for desktop, and it is low cost, but still supports the short-range wireless standards used with Nordic devices. And the dongle has been designed to be used as a wireless hardware device with the NRF Connect, which is an SDK. Um, Eventually, I might end up actually having to explore the NRF Connect SDK through this series. I'll be doing this NRF Power Zephyr mixture um, series for let's say I think I'll be working on this for another week or so, maybe even two. and in the end, we might end up exploring NRF Connect. And when we do, I will label the stream as such. But at the moment, I don't know when we'll be doing that. So from that basics, it's just wireless. It's a wireless system on chip. It supports. It has an integrated on-chip radio, which is quite cool because then you're not your radio and your CPU are in the same block, and it basically all you need to do is hook up a antenna and you can basically start processing stuff. Um, so I went through this document, which is the NRF52840 reference manual. Uh, there should be an about this document somewhere. So this is a reference manual for the system on chip that we are exploring. And what the reference manual basically tells you about the system on chip is it tells you about it shows you a block diagram, and the block diagram happens to be let me know if I need to zoom on this or something. But the block diagram happens to be the whole system. So the whole little this block diagram shows where's my thing. This block diagram shows that that black square on the board, which is the microcontroller unit. Okay, so the MCU and all the peripherals that are in there. And if we explore here, we'll see that you have some debug endpoints on this side from SWIO and SW clock. So you can use SWD debugging and deployment with this. And then we can see it has an ARM Cortex M4 CPU, which is quite standard. That's kind of my favorite one at the moment. And then attached with the ARM standard is the SysTick peripheral and the NVIC, which is the nested vector interrupt peripheral controller. And then we have an AHV advanced peripheral, I think, so that we can split it into AHV and the PB, I think. I might be wrong about that. I might not remember correctly. And then we have a watchdog timer and PPI interface, and then a lot of other interfaces. But today we're going to basically explore the PPI interface. We're going to explore the radio interface, which is over here. And I think along with that, we might pass through the power management unit, which I don't know if it's shown on this because it's basically in between the power management unit might end up being out of this block. So because let's just go and look at things. So you see, this is the PMU, and then there's a CPU, there's a memory, there's a peripheral, there's memory, there's peripherals, there's a CPU, and then there's a PMU, and then there's all these regulators and stuff, and then there's power. So basically, looking at our block diagram, when we look at where the power sources are, uh, power sources. So here, somewhere here, VDD, VBus, VDD plus, somewhere here, past of this is going to be the power unit because as you can see, CPU, power into CPU and power into memory and such, and then that is in there. So we're going to be in essence, we're going to explore those three systems: the power management unit, and then the PPI interface, or rather PPI peripheral, and then as well programmable peripheral interface. That's what um, uh, the PPI means. And then we're also going to explore the radio. So let's see. Yeah, yes, for sure. Okay, cool. So let's think about this. Um, in fact, um, let's look at let's look at. I have a link out there to this. I shall add this to the description of this. Uh, I shall add this to the description of this stream. And basically what is going to happen is you're going to be able to have it. I'll add this to the description. And ah, where do we do that? And, I'll share it in the chat, and then I will add this to the description. I have some notes that I've done while I was preparing for our our thing, our our stream today. And let's start. So let's start by just we've gone through the notable features of this system on chip. We know it has Bluetooth. We know it's ideal for with applications that can use that radio and applications that need to use that radio in low power situations because it has a very involving low power system, which we'll explore just now, which also kind of makes it worse to do power management on because there's this whole tuning uh, system on board that basically I don't know if it uses reference cards or something, but it checks how many devices are being used, and then whenever a device is not being used, it basically turns off that device, and then it also checks how many what device depends on which clock and on which power source, and based on the availability of that clock and that power source, it will start or stop that device. So this makes it a little tricky to measure. Uh, Obviously, we do have the stable workhorse, which is the STM32F4, and if need be, we can do our experiments because it even has an exposed measuring pins. Amazing. So let's think about this. So uh, we have support for over the air download firmware updates. Okay, so we can send firmware updates over the air to this thing. That should probably be one of the things I'll do later. To try and send firmware updates via Bluetooth. We have a Core M4 running up to 64 megahertz with FPU with a single point FPU and DSP extensions. It's this core supports 8-bit and 16-bit single instruction multiple data assembly. So you can use this for signal processing and such, which coincidentally happens to be what we're going to be doing a lot. And then uh, if you explore the reference manual properly, you discover that this application has you can run you can do execute in place, which is Control F slash executing code. Wow, it just goes straight to executing code from flash memory will have a wait state payment. Forget all of that stuff. Basically, what this CPU supports is execute code from flash. This means you can effectively uh, execute code where it is rather than having to copy it over into RAM or into someplace else or some cache somewhere to run it. Okay, cool. So this also has secure boot that's further advanced by the cryptographic accelerator that's on board. The cryptographic accelerator basically enables you to do things like checking that the firmware is the same one that you should run and doing cryptographic communication with something like TLS or SSL and so on and so forth. And basically, this makes those cryptographic uh, calculations faster so that you can do them at low power with low budget. See, so when you get to MCUs, you'll hear this budget thing. So the budget thing can be split into a number of factors. It could be either the space that you need or the power that you need. So if you need a lot of space, you have a high budget for space or for memory. And if you need a lot of power, you have a high power budget. And then you will notice a lot of think a lot of sales material will try and push low budget, low link budget, low power budget, low memory budget, and that means do very you can do a lot with very little space. Basically, that's what it means. So, and then obviously I discovered this supports QSPI. I did not know that. And then we have an NFC field detect, NFC FDT, which can be used as a wake up source. So basically, this MCU can walk into and it could be in sleep mode with the appropriate peripheral settings. It could be in sleep mode, but you could enter an area with an NFC network, and this NFC network would enable it to start up. Um, just a moment. Okay, so you can enter an NFC network, and this thing will be enabled to start. Basically, you can wake it up by entering it by detecting a network. Excuse me. We have an 1 MB flash on board. We have 256 kilobytes of RAM. We have an EasyDMA peripheral, which I think that um, deserves to be shown. Block, block diagram. Oh, now I know how to go back to that. Just toggle off that. So we have an EasyDMA, what do you call it? EasyDMA, can you, yeah. We have this EasyDMA peripheral that is connected to all of the, not all of them, almost all of them, almost all of the other peripherals. What this enables is connecting these peripherals with each other in absolution of the um, in absolution of the CPU over here. Um, yeah. So let's go back to that document that we are looking at, and I will mute just for a moment. So my word. I've been talking so long without the mic. I apologize about the lack of audio in the last few minutes. So, whenever you're exploring wireless devices, it's key to make sure that one of the key factors is to make sure that power management is something that you explore very deeply. The reason being is because wireless devices are largely battery powered by the virtue of being wireless. That means they're not connected to some power unit all the time. So they're running on battery. They need to run in low power states, and then you need to be able, whatever device you're exploring needs to be able to go into low power and come out of low power. So one of the first features you will look for in wireless applications is checking whether they have uh, power states. Okay, and then if they do have power states, do you have ways of going into those power states and coming out of those power states? And when I say power states, I mean something like system off, system on. Um, let's see if we can't find where power states are. We could just touch power. So basically, I think these are more defined in uh, the Cortex ARM reference manual more than they are more than they are defined in. Let's look at the ARM reference manual. See, I should have it. What what are you? What are you? No, this is the ARM debug interface. I probably have a browser open. ARM Cortex for power. Can you be a PDF, please? Can you be a PDF, please? Mm. System control. Can I control the system? Please, can I search? ARM M for power. Please show me power. Please show me power. Power, 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 power. Yeah. System control. Should be power registers here. Just a moment. So wait. Basically, Cortex M4 power modes. I can just look at it here. Just a moment. Sorry about the mic again. Okay, so there's a few system power modes, and basically Cortex M4 supports those three, as you've seen. So the Cortex M4, every microcontroller that is based on the ARM Cortex M processor will have at least three power modes: run, sleep, and deep sleep. Okay, so our our the system that we're exploring today, the NRF52840, has two two main modes. So the system off mode, which is the deepest power saving mode the system can enter. And in this mode, the system's core functionality is powered down and all ongoing tasks are terminated. Okay, so let's look at this. The system can be put into system off using the system off register. We can explore that later when we're looking at actual code. First of all, let's actually see how this works. And then the device can be woken. The system can go into system off mode using that register, and then to come out of system off mode, we have a few wake up sources. The detect signal, optionally generated by the GPIO or the LP comp or the NFC DT that we talked about. So detect signal can be generated by GPIO peripheral. The analog detect signal can be generated by the low power comparator module. So this is a module that checks, the LP-COM module checks how much power it basically has a reference signal, and it checks if we go above the reference signal by a certain margin, and if we do, it can basically do this if enabled. And then the sense signal, optionally generated by the NFC detect wake-on field, can also move the device out of system off mode. and then valid USB voltage. So powering this device via USB also can move it. And then if you do a power reset, there's a reset button, can also move it out of system off mode. Okay. The system is reset when it wakes up from system off mode. So this is what happens basically when we leave off mode. Excuse me. Excuse me. Wow. Okay. Cool. So whenever we come out of system off mode, the system is reset. So let's look at system on mode. System on mode. System on is the default power state after power on reset. In system on mode, all functional blocks such as the CPU or peripherals can be in idle or in run mode, depending on the configuration set by the software and the state of the application uh, executing. Okay, and then system on mode itself has two sub modes. So the sub modes are constant latency and low power. In constant latency, you basically have the same gap of time between when you demand. Let me just check that my audio is good. Um, you have the same gap of time between when you demand the CPU and when you get it. Okay, and basically this is run mode. If we think about the three Cortex M4 Cortex M power modes, this is run mode. You basically have the say you know how long it will take between you requesting the CPU and getting the CPU. So the latency mode, okay, constant latency. Basically, the power is always the system is always on and waiting for your thing. So it will take at most this much time to get the resource that you request. And this is secured by forcing a set of basic resources to be turned on while in sleep. The cost the the cost of constant and predictable latency is increased power consumption. So power constant latency mode is selected by triggering the cons late task, okay, which is a task that we will explore later. We are looking at the PPI interface. And then in low power mode, the automatic power management system described in the system on module ensures that the most efficient supply option is chosen to save power. So in low power mode, you don't know how long it's going to take between you requesting a resource and getting the resource. But there there could be this there could be some limits that have been defined that help you when so that you know it could take up to this long. You see? But basically what happens in low power mode is that the system is basically put in a soft off mode, and then when you request a peripheral or when you request a peripheral or a resource, it's quickly turned on and then it's provided to you. The cost of this is that we don't know exactly how long it will take to get these resources because they're off. So that's the cost. The benefit of this is that most of the time, these resources are switched off. So you have a better power mode. You can store power better. And if you think about it, that enables us to cover the three uh, power modes that are demanded in all the Cortex M processors. So run is taken care of by constant latency mode. Sleep is taken care of by low power mode, where they're mostly asleep, but when you do request them, they will be provided. They will come on, and then you can use them. And then deep sleep is taken care of by system off mode. And in system off mode, In system off mode, you can only come out of system off mode, or rather, you can get only get resources back when the detect signals, the it depends, the detect and the sense signals are enabled and are given. Anyways, there is some notes on this. The link is on the link is in the description and on the chat of this, and in which I've described the power states and the wake up sources. Basically, you can wake up from the wake up interrupt controller. I'm sorry, the analog or digital wake up pin on the power supply system. The low power comparator can be used as a source, as a wake up source. So basically, it can get a signal that makes the system move from system off to system on, and then NFC detect. Um, we can actually go through all of this. Um, such wake up source. Okay, cool. So let's go through all of them. There'll be few. There won't be too many. So the low power comparator compares an input voltage against a reference voltage. So this is a peripheral. This is a peripheral that uh, go back to the block diagram. The LP comp, LP comp, LP comp. So there's this LP comp here, and this peripheral basically what it does is it compares some incoming voltage against a reference voltage. And if the incoming voltage is, depending on what you set it to do, if the incoming voltage is so much is higher or low, it's if it breaks a certain threshold, okay, if it breaks a certain threshold, um, then it disallows the low power comparator to send a wake signal to the system, which makes the system move from system off to system on. That's basically said here. Additionally, the low power comparator can be used as an analog wake up source from system off or system on. Okay, the comparator threshold, which is the distance between the reference voltage and the one that the reference voltage and the input voltage, that can be programmed to a range of fractions of the supply voltage. Okay, cool. That's one. So there's that. Let's look at another. Wake can be triggered from the ANA detect here, and then we also wake up can detect signal. So yeah, so that's the wake up that, and then wake up can also be caused from the interrupt controller. So where is that? Analog or digital wake up pin from the low power comp. Uh, wait. Just go slowly. Wake up from system off. This is another. That's another task. NFC dip. Yeah, NFC DT. So as described earlier, the NFC field can detect NFC network, and you can set the system so that when it detects an NFC network, it will um, send a wake up signal, basically. Okay. The NFC low power field detect function can wake the system through a reset. So basically, the NFC can detect a field and then push the system into reset. Boom, you have a wake up source, and it's a wake up source. And then I know that the analog in, but that's from the LP comparator. And then which other ones? Which other ones did we see? So LP comparator, analog or digital from power supply system, LP comparator, NFC detect system. That's really all of them. Um, let's just quickly brush through, quickly brush through, quickly brush through. Yeah, So we know what power modes this device has summarily, okay? Summarily, not in practice. In theory, we know what modes this device has, and we know how to go into the power modes, and we know how come out well low power modes. Anyways, power modes. We know how to go into the power modes and come out of the power modes, which this is important because this is going to be key when you're making a wireless device. One of the things you're going to do is do a task, go into low power, do a task, go into low power. You don't want to stay in high power as much as possible. You don't want to stay powered as much as possible. You see, any question? The crickets are chirping. Crickets are chirping. Okay, cool. So let's check out the other thing. The next part we wanted to explore of this system, or yeah, of the system on chip is the radio system. So the radio system. So this, first of all, if we look at about this one, content features. So one of the main selling points about this little system on chip is the it comes with a radio peripheral. And the radio peripheral on this chip is able to can conform to quite a few standards. Excuse me, let me go again. I should have NRF document somewhere. Yeah, so this one. Just excuse me for a moment. And I'm back. Thank you. So one of the main selling points of this system on chip is that it has an on-chip radio peripheral. And the on-chip radio peripheral enables you to do a number of things. So first of all, the on-chip radio peripheral is capable of Bluetooth 5.2, which comes in with the Bluetooth Low Energy, and it comes with both Bluetooth at 1 megabits and Bluetooth at 2 megabits, plus long range. And I think advertising extensions and such. Number one, and then this same radio allows you to do IEEE 802.15.4. This is the thing that has thread. It has Zigbee. It has basically I. This was designed for IEEE. Yeah, here it is. So this was designed for low power, low rate wireless personal area networks. So basically, an in-home network, or an in-factory, or an in local network, an in local low rate wireless network. It's low rate so that you can do wireless stuff on it, which is battery powered, and then it's also personal area because it's that small, but you can use it. It defines the physical layer and the media access control layer, and then beyond that, you can build up whatever protocols you have on. But basically, this is what was used. This is what is used to power things like Zigbee, Thread, wireless HRT, MIWI, six low PAN. What's that one? Six low wireless power area network. Okay, so from the ITF, Andrew and them should know about this more. But yeah, so this radio on this device can manage those. So Bluetooth Low Energy, Bluetooth Classic, uh, Zigbee, Thread, and all the 802.15.4 associations. And then in addition to that, we have NRF proprietary radio for proprietary radio implementations, both 1 megabit and 2 megabit from NRF. This our device supports that. And let's just jump onto the radio description a bit more so that we can jump on it better. Uh, let's go to the radio. So peripherals, DVI-T, no, Topicon, no, NFCP, no. We want to look at the radio so that we know what the radio does. Cool. So the radio transceiver is compatible with those multiple radio standards that I've mentioned. And then the main features are it's a 2.4 gigahertz radio transceiver. It's got 1 MB and 2 MB modes, long range and Bluetooth energy mode. And then it's got a 250 kbps 802.15 mode. And then it's got two more 1 MB and 2 MB Nordic proprietary modes. So basically what this means is you can do quite a varied range of applications and connections with this. And we can see it says best. You could even have um, you could even have a small network of devices connecting to an outside devices. So think about it this way. You can use, if you have two headphones, say two earbuds or whatever, your earbuds could be both connected by a different radio, although this might be heavy for, it also might be heavier, it might be cheaper, but they could be both connected by a different radio protocol, both of them, because they do need, one of them is the main and one of them is the main and the other, one of them is the controller and the other one is the controlled, usually, sometimes. Uh, Basically, you could have them talking on a different radio frequency or a different radio protocol, and then you could have the main controller talking to your mobile phone via different. So you could have Bluetooth Classic from this to this, and then Bluetooth Low Energy from this one to this one, basically. You see, whenever the main or the controlling device does not, or rather the gateway device. Yeah, let's talk about gateways and receiver. The gateway device does not have, um, the gateway device does not support Bluetooth Low Energy, basically. Um, yeah, so that presents quite a varied way of, you can control this. And then, if I recall correctly, while looking through this peripheral, first of all, it's connected to EZDMA, and it's also connected to PPI, which we will explore just now. But EZDMA allows it to be connected to quite a few other combinations of devices. And then besides that, so there's a few easy wins that come with using this radio. Number one, it includes whitelisting, um, which is basically, it uses pattern matching to recognize known addresses, and it can communicate with them quickly. So there's less power used in doing authentication, something of the sort. And then it deals with timing and space interframe spacing. So spaces between frames in your Space, the timing between frames when you're doing the timing between frames can become very heavy computationally, and because the radio itself can deal with interframe spacing, your CPU does not have to do those extra computations to determine what frame is which frame. The radio does this for you. So basically, you have a little radio that does quite a bit of pre-processing for you, so that when you get the frames in the CPU or in in some other peripheral, they've already been slotted into the right places, and you're just consuming them or just doing computations on the frames themselves, rather than preparing the frames then doing that. So the radio can aid you to a certain extent in preparing the frames. So let's just rattle these things quickly out. So the radio has a multi-domain transceiver. It has a low link budget plus low power operation modes. It's with EZDMA, it makes it you can do something like good from another peripheral. Let's look at it. This is easy. This is easy. Yeah, remove search to bar diagram. So let's look at the PDM peripheral, EZDMA. The radio peripheral, please tell me how to EZDMA. I imagine it did, but I always miss it. Seems like it did not. Yeah, what am I saying here? So the radio peripheral has EZDMA, the PDM peripheral has EZDMA, and they're all connected by the APB0 bus. Okay, hang on with me there. So you can, in theory, implement an application using a PDM microphone. So it collects mono stereo information, mono stereo samples, and this can be collected into the PDM microphone, pushed into the radio, and out of the antenna without the involvement of the CPU. And what does that mean? That's a little sketch I did here. So it allows us to interface other peripherals with the radio uh, uh, and do you know do application stuff without actually putting in the CPU. And I've already mentioned it has automatic address filtering and pattern matching, which makes it easy to whitelist addresses and simplifies the calculation of uh, spacing in frames so that the CPU has less work. And then it includes a bit counter so that it knows how many it can make pockets and stuff. And then also includes a RSSI indicator, which it can use in other calculations. And basically, there's a little rattle there of how to choose which mode, but this will come in depth. I mean, right now we're just looking at overview of the CPU or of the system on chip before we even actually start using it. Okay, cool. And then in the end, we have PPI, and sometimes in Nordic or in Nordic circles, it could be also DPPI. The PPI is a programmable peripheral interconnect, which allows peripherals to interact with each other independent of the CPU. If you hear that, isn't that like sort of DMA? That's how I'm looking at it. I'm still understanding it, but the essence is that you can. It allows this is not just simple memory copy from one end to the other. Basically, you allow this to do some computation. You can allow some computation to happen through this peripheral interconnect. So basically, Let's go back here. I've said basically so many times. It is basically. That's the problem. We're building up from basics all the time. That's why these things are hard. Always working from very base peripherals. I'm muting again. Today has been difficult because of my nose. I've basically been on and off every few minutes, and I keep doing every few 10 minutes without talking, or rather in mute. They'll only get better from here. So I'm quite keen on PPI. I don't understand it very well yet. Um, I still need to know what sort of pre-programming you can do with a PPI channel. NRF PPI example. So I'm just reading up on what this thing does. Okay. What is PPI? Why might it be useful for your project? PPI terminology, tasks, events, and channel. How to include. Mm, okay, okay, okay. So the compiler, right? Okay, cool. The NRF is the NRF52 PPI. So PPI stands for Programmable Peripheral Interconnect. As the name suggests, PPI model allows two peripherals to communicate with each other without CPU intervention, as illustrated now. Peripheral 1 into PPI module into peripheral 2. You can imagine the PPI module as configurable wires that connect two peripherals. Configurable means you can choose which peripheral to connect at one end and which connect at the other end. Okay. You can use PPI in applications where if peripheral 1 finishes some job and you expect peripheral 2 to be automatically notified and triggers an action. For example, peripheral 1 might be a timer peripheral which generates an event every 500 milliseconds. Peripheral 2 might be GPIO TE module that controls a GPIO pin connected to an LED. Whenever whenever the timer that whenever the timer peripheral expires, the GPIO pin is toggled so that the LED blinks. You can connect timer events to one end of the PPI channel and GPIO TE tasks to the other end of the same PPI channel. That configuration allows the LED to blink every 500 milliseconds without CPU. This seems like DMA still. There are 32 PPI channels that are available to use. Of those 20 channels, 0 to 19 are configurable. 12 channels, 20 to 31 are fixed. Yeah, that's all of them. You can choose which peripheral to connect to a configurable channel. However, you can only enable or disable a PPI fixed channel because its connections are fixed. Uh, so you enable the PPI, you allocate a PPI channel, and then can we look at this in something I already understand? Example. I'm trying to look for a PPI sample. Zephyr. Let's see. PPI supported in Zephyr. Should be. Mm, PPI. Might not be. Oh, it is. It is. Any sample. Any sample. Mm, You know what I usually do is you take that and you search it in Zephyr. Nordic NRF. What is it? NRF-PPI. If there's any samples that use it, we might end up getting it. Sys releases, sys releases. That's the actual thing itself. Mm, mm. Um, Maybe we have samples in memory management. Maybe there's memory management samples. Mm, I like this one. These are eating philosophies, but also synchronization. What are they? That one. Mm. I don't. Maybe we need to build a PPI sample. Mm, mm. Okay, it seems we do not have a PPI sample in and this one is using a very contrived, simplistic. Sorry, that would be awesome. I don't know. I don't know. Nordic PPI plus DMA. Hmm. I need to dig into more. I need to try and to build. I need to try and build a PPI sample application just so I understand what PPI is and the difference between PPI and DMA. I reckon that's what I need to do. I reckon that's what I need to do. Okay. Excuse me. It's been more than an hour. It's been an hour, 20 minutes. And what we've done today basically is we have explored the Nordic NRF 52840 and we've explored it for basically we've done NRF 52840 evaluation, power and radio evaluation for LP application. Yeah, I think that's what we just did. Um, can I edit this? NRF 52840 evaluation radio and power valuation for no power application. How the NRF 52840 implement low power and radio in order to later I'll add yeah okay let's add what document was that we looked at. Let's add all the documents we looked at. There's this log. Okay, and then we need to add this NRF 52840 reference manual. Excuse me, let's add a link to that. Can, can I grab a link, copy link address? Let's put it in there. Okay, cool. So that's okay, that's fine. That ended up being what we did today, and I'm quite thankful. We've updated that. That already has that. And then we do indeed go back here. Create that. Okay, cool. Ooh. Yeah, people came in. Thank you so much for attending today. Sorry about all the audio problems. And tomorrow we will be working on what is it that we're working on tomorrow? We might actually do power management in Zephyr on the NRF tomorrow. But let me actually uh, let me actually stream this. So yeah, we look flow power management in Zephyr on the NRF. But thank you so much for coming today. That has been amazing. I'll go and drink some medicine, and then I'll see you guys tomorrow. That was amazing. That was an amazing exploration.